All right, Chloe, we're starting 2-4 notes. I don't know, we'll see how far we get. But we're doing scatter plots today. We've done a lot of graphs so far, yeah? We have done, starting off this chapter, we've done frequency tables, which led into histograms, right? Okay, histograms are the bar charts that have to do with frequency tables. Then we did like dot plots and stem and leaf plots and pie charts and Pareto charts and frequency polygons and all of those things, right? Goodness. I choke on my own spit here. No, I need some more liquids here. My milk is gone. All right. Now we're on to scatter plots. Okay, do you know what a scatter plot is? Yes, yes. Usually in a scatter plot, none of the dots are connected. So here's an example of a scatter plot. It is a lot of data all up there on the board. Okay. Different from a frequency polygon. A frequency polygon would take the midpoints of classes and like do some things like this, whatever, right? Okay. But on a scatter plot, all of the data is there. True? Each one, like I could find each one of those data points. Whereas like a frequency polygon, a histogram, all of those things don't have it. What are you doing? You don't need that. So I could find all those data points. They are all listed on a scatter plot. All of the dots are there, right? Okay. So we're talking about correlation. All right. And we've discussed this word before, but if two things are correlated, what does that mean? Has a relationship. Like two variables have a relationship. Okay. Now, a linear correlation means that they have a linear relationship. Okay? Because you can have a relationship that is not linear, right? For example, if I'm graphing two things and like this type of thing happens, what kind of relationship is that? That's not linear. What type of a relationship is that scatter plot? What does it look like? It looks like one of these, right? It's not necessarily a bell curve. It's a parabola, right? And a parabola is a quadratic, right? It could be a quadratic relationship between the two, right? If he's doing like a parabola or a something like that. But a linear relationship is going to look like this. If you want to write this down. Something like that, where you could draw a straight line and it kind of like resembles a straight line, right? With the side effects and all, or the sound effects and all, right? That is a linear relationship. All right, scatter plot is a plot of all data points. Scatter plot, a plot of all data points. Okay, now, caution, circle this really big. Whoop, I think this was on your last test, wasn't it? Okay, just because two things are correlated, just because there's a relationship between two things, doesn't mean that one causes the other, true? My very big example is ice cream. Ice cream sales versus drownings. Drownings. D-R-O-W-N-I. Let me start again. Let me try again. Try again, Mrs. Comacher. Drownings. D-R-O-W-N-I-N-G-S. Is that drownings? Probably. Okay, so ice cream sales go up at the same time that a lot of drownings increase, right? No. Does that mean eating ice cream causes you to drown? Yeah, like it would make sense, right? No.
It makes
No.
you fat, so you sink to the bottom.
There is something called a lurking variable. Here, right. A lurking variable, and that lurking variable is what? What's the lurking variable in there that connects the two? The heat or summer, right? I'm going to say, yeah, I like that. Heat, right? When it's hot out, ice cream sales are going to go up. When it's hot out, drownings are going to go up because more people are swimming, right? So just because those two are increasing at the same time does not necessarily mean that one is causing the other one to happen. This is like a huge issue right now when people are trying to look at correlation between COVID numbers and something, right? Like COVID deaths versus this, okay? They do this a lot with vaccines. Like comparing vaccines versus autism. That's a huge one. We watched a TikTok on it or whatever. So like a lot of people think that vaccines cause autism because there is a spike in the number of vaccines that are produced and there's a spike in the number of like autism cases. Okay? Just because they're both going up at the same time doesn't necessarily mean one's causing the other. Okay? So that's what they're trying to decide. Just because there's a correlation doesn't mean that one is causing the other one, or like, are they completely two unrelated things that are happening at the same time, right? Now, maybe vaccines do cause autism. I don't know. That's why we have to study it further, right? We have to look at the graph, look at the correlation, and then we're going to do some more data analysis to figure out, okay, is one causing the other? Because if it is, we've got to do some reform to our vaccines and fix it. Or if one's not causing the other, let's clear up some of the mud in here and educate people so that they know that like vaccines are not contributing to autism, right? Because a lot of people think that they are. I don't know where you're at on that political opinion, whatever, but, and I don't know what the answer to that is either. But that's why it's important, and that's where we're at right now, is a lot of people are doing studies on autism and vaccines, okay, to try to prove one way or the other, okay? So there's that. Correlation does not imply causation. Here we go. Example 1. Correlation. We have a waist and arm circumference, okay? Your waist circumference is the distance around right here, right? The distance around your waist. And your arm circumference is the distance around here. Now, for the most part, in general, like if we're looking at kindergartners who have small waists and small arms versus like you guys who have a little bit bigger waists, you're not fat by any means, but you have bigger waists than a kindergartner, right? And hopefully bigger arms, right? You're a little more muscular, right? In general, it's going to show a positive linear correlation. Write that down. Positive linear correlation, right? Positive linear correlation, right? For the most part, as waist circumference, as the size in your middle increases, your arm circumference is going to go up, right? Slightly, okay? Now, we are going to have some weird anomalies that happen, right? You have those bodybuilders that are like super skinny right here, and their arms are like massive. True? Those are going to be the people, let me find a dot, that are like right here. These are my bodybuilders. True? That dot that's way up here at the top has a high arm circumference, but a fairly low waist circumference, right? They're like kind of here in the middle waist circumference-wise, right? Those are my bodybuilders, okay? Now, you're also going to have probably some people that are really big around the waist that are really wimpy on their arms. Now, you do accumulate fat in your arms, so I'm not going to say that like your arm circumference is like, but you might have a smaller arm circumference if you're 300 pounds and don't lift weights versus somebody who's 300 pounds and does lift weights, right? Okay. So, waist circumference, these might be our stubby people. Is that like a generally nice term to call like a really fat person? Okay, stubby. We'll call him stubby, right?
Call him
Stubby would be the dot way up.
I don't
know.
I don't know. Well,
Just
sure. But honestly though, short and fat, their waist circumference will be, yeah, honestly, like you put my weight on a 6 foot tall person and they're gonna be like anorexic looking, honestly. Really? Like really, like it's not fair. Oh, stomp my foot. It's not fair, right? If I was taller, I would be way skinnier than I am now. Not fair. Not fair, right? So the stubby people, the short ones and the fat ones, they're going to have a large waist circumference. They're going to be all the way over here, but they're going to be kind of down lower on the arm circumference because their arms are not going to be as big as a bodybuilder. Right? What?
We have not seen the same fat people. I don't know what fat people you're seeing with small.
Have you
arms.
seen?
1,000 pounds.
Have you
No,
seen
I'm
Aiden?
saying, hey.
Yeah, she has weight.
But really though, Remington, look at this. This stubby, like fat person, their arm circumference is not all the way down here, right? But they're not going to have the arm circumference of the same weight of person that's a bodybuilder.
Where
True?
are they measuring? Are they measuring here?
They're measuring up here, I think, their bicep area. Is this a bicep? Is that what it is? Right? Okay? So do we see how this works, right? You may end up having some weird things happen, but for the most part, as your waist size goes up from birth, right? As your waist size goes up, your arm circumference is going to go up, right? Yeah?
And
Which
fall.
one changes at a faster rate? Waist or arm?
Waist.
Waist is going to change at a faster rate, right? This is a lot like different compared to a little kid versus this being compared to a little kid, right? Your waist is going to change at a faster rate. Got it?
That's why so many toddlers are chubby.
You think?
Your
Yeah.
fat
Yeah.
goes to your waist first usually.
Your fast goes to like my kids, like they're like I could do this around their arms, like all the way up here. Like that's so tiny. Like, you need to eat more. I tell my kids that. They really do need to eat more. Okay, so that is a positive linear correlation. Did you write that down off to the side over here? Positive linear correlation. Yes? Okay, positive because why? It's trending uphill. Can we have a negative linear correlation? Yes, it would just do this, and we'll see that here in a second, right? But it's still correlated. Those two things are related to each other. Now, we have to decide, okay, that's correlated, right? But is waist circumference, increase in waist circumference, causing your arm size to go up? Is there causation that's happening here? Do you think there's causation happening here?
No.
You don't think your waist size increasing causes your arm to increase? I think it does.
No, it's just the fatter you get, the bigger everything is. So it's like,
That's what I'm saying. One causes the other, right?
Technically,
Yeah?
no,
I don't think
it's what you're
necessarily.
eating
No,
that
because-
causes it. Because your waist doesn't cause your arms to get
no,
bigger.
but if you're
What you
working
eat-
out, if your arms are getting bigger, your waist isn't gonna get bigger.
Okay. All right. Okay. All right.
It's just correlation.
Okay, example 2. This one is an example of no correlation. Let's see what we are comparing. We are comparing your weight and your pulse rate. What was your pulse rate? Do you remember?
60,
175 kilograms is like over 300 pounds.
Jack?
like,
And how much do you weigh, Jack?
I just weighed myself this morning. 196.7.
Okay, Jack weighs more than me. All right?
I'd hope.
really?
Okay, whatever. Jack weighs more than I do. I don't know. I hide a lot of weight in places. You guys would be surprised. Okay, Jack weighs more than me, but his weight is lower, or his pulse is lower than mine, right? Mine was like in the 112 or something.
Well, maybe
Nice.
you weighed off the Dr. Pepper, dude.
I haven't had a Dr. Pepper yet today, kid.
Yet.
It takes a
Give it
lot
50
of
hours
energy
and
to
you'll be
stand
up
up
to
here and
your-
talk at you for all, like,
That's
whatever. Okay? Yeah, see? He should have a high pulse because he's got
I
energy
train my
drinks
heart.
like
But he
crazy.
doesn't drink like
You what?
3 a
I
day.
trained my heart. Oh, you would be
That's,
surprised.
no, he drinks
Okay.
a lot, and that's much more fast.
So, do we see how these two things would probably not be related? Right? Your weight has nothing to do with what your pulse rate is. Okay? Yes, yes? Now,
But normally, if you're overweight, then your heart has to
Those
try
have 200?
But
I thought those had
true,
100.
but does that mean it's beating
Not
faster
the
though?
money.
Or
I
beating
thought those had
harder?
like 110.
That doesn't necessarily mean it's beating faster, right?
But they were, I drink Monster.
Now, you do have some people down here on this end, like these people, are going to be the, like, swimmers. Like I'm talking about, like, ocean swimmers, right? Like, people who swim across oceans. Did you know that those people who swim across oceans, they condition their heart to be, like, in the 30s, their heart rate to be in the 30s? Did you know that? Did you know you can condition your heart to be that way? Cross-country runners, people who run long distances typically have a lower heart rate,
My
okay?
resting heart rate
So there
42.
is a little bit of some weird things that happen in there, but in general, weight and pulse rate do not have a relationship between with each other, right? No correlation. Got it? All right, here's an example 3 again. You had a question like this on your homework assignment. Shh. Clusters and gap. Here we're talking about the weight of pennies and the year in which they were produced. Okay? So in the earlier years, that would be like down here, right? These are early years. Early years equals heavy pennies. Right?
But they're not that heavy.
Well, they're heavy. Which one's heavy, copper or zinc? Do we know?
I think it was the copper one.
Copper was most,
The
okay?
zinc.
So most copper.
No, I wouldn't.
All right. So in the early years, they were mostly made of copper. Like it was like 85% copper, 15% zinc, right? And they were heavier pennies. Then in the later years, we started making them out of a zinc. We flipped it, so we did 85% zinc, 15% copper, and they were less weight, right? So they went over here on the scale of weight, and then went up higher because they are whatever, right? So that is an example of a cluster and a gap that you can see with the scatter plot, okay? But again, this is telling a story and we can see that there's a relationship somewhere, and we need to figure out what it is. Got it? All right, here we go. Go to the bottom of that page. I'm going to give you a scale, and I want you to write it down. I know it's written down on the top of the next page, but I want you to write it down. Here is the correlation coefficient R. Okay? R is our correlation coefficient. That's what we use to represent how two things are correlated. Okay? R must live between the numbers -1 and +1. Okay? 0 is in the middle.
I remember this.
All right? 0 is in the middle. If you have an R value that is really, really, really close to a +1, here's what's happening. Write this graph down.
Close to the trend line.
It is doing this. Like it's really, really, really close, and my line is really, really, really close to all of the dots. That's a positive linear correlation with an R value close to 1, because almost all of those dots live on that line, yes? Okay? All right, if you are really, really, really close to a -1,
It'd be straight.
Jace, listen,
I'm
turn around.
literally discussing this.
Okay, if you are really, really, really close to a -1, you look like this. Okay, your dots are still really, really, really close to the line, but it is a negative slope, right? Okay, give me an example of something that like goes down and has a negative linear correlation.
Vehicle values.
Yeah.
Okay, sure, yeah.
Yeah.
Yeah, so like time would be on this. Yeah, nice. And
Good boy.
of a car. Cost of a car, right? So the cost of a car is going to go down in value. Now you might have something weird happen where you have like a very rare vehicle that like as time increases it might go up in value. You might have some dots that live outside of that line, but for the most part you're going to have most of those dots living on a straight linear like depreciation scale, right? Okay, that are going downhill. That is going to have a correlation coefficient of something close to -1, like it might be like 0.998 or something like that, right? Very, very close to that line where it's depreciating. Got it? If you have an R value that is like, let's say like R equals 0.2, not a very good relationship. That is going to be something that looks like this. All over the place. Not a very good linear relationship, right? Like if I try to draw a line in there, sure, it might go like this, but how many of those dots are living on my line? Not very many, right? Okay. So 0.2 might end up looking like this. -0.2 would be the other direction. So like I might be able to draw some dots that are kind of going downhill. I don't know, like this, right? Negative linear correlation, but not very close to, that would be like an R of -0.2, right? Not very closely linear, not very close of a linear relationship, right? Good, good. Okay. That is what happens. Now, how do we get an R value? We plug our data points into like some sort of technology, and it will spit out an R value to us.
Sheets.
What?
Google Sheets.
Google Sheets is what we're going to do here in a little bit. Yeah. So an R value. All right. They're going to have us do some stuff here. This one, correlation between shoe print lengths and height. Okay. Do you think your shoe size is correlated to your height?
Yes.
Kind of. Yeah. Right? But we have some weird things happen here, like we were talking about shoe size. Like he has a way bigger shoe size? Smaller. And he's taller than you, right? Slightly?
No.
Or no?
I'm taller.
You're
Our
taller?
feet are the same length, but he has a bigger shoe size.
Oh, gotcha. So you are the same shoe length, or foot length, but you are taller, right? So we might have some weird things happen. Like I prefer a size like 7.5, but I might be the same foot size as like Hallie, who prefers I don't know, an 8, right? So there's going to be some weird things in there. They say that this data right here has an R value of this. 0.591. Is that a linear relationship?
It's all right.
Right? The scale goes from, again, -1 to 1. The closer it is to 0, the worse the relationship is. So this is positive, right? It is showing a positive relationship, but is it a strong positive or is it a weak positive?
Middle.
It's like midline, right? So here's the problem. Where is the division, right? Like where is the cutoff that says strong versus weak? This is strong positive, this is weak positive. Where is the division line?
0.499.
The answer is
There isn't.
It depends. Now, it depends on how many data points you have typically, right? If I have not very many data points, I should be all the way over here, right? If I have a bunch of data points, right? I might have a little bit more leeway. So here's the deal. Let's go to this guy right here. If we have 4 data points, right? If we have 4 data points, what's considered to be a strong relationship is 0.95 and above, right? If I have 10 data points, anything above 0.63 is considered strong. Does that make sense? Yeah? If I have 7, anything above 0.75 is considered strong. Does this make sense? Yeah? Okay, so looking at this guy right here, the fact that I have 0.591, R equals 0.591. Strong, what's considered strong? A strong R for this guy right here. How many data points do I have? 5. So 0.878. 0.878. So is this a strong positive or a weak positive?
It's weak.
It's a weak positive. They might even say no correlation, right? Okay? So weak positive, they might even say no correlation. So here, it has to be above 0.878 in order to say that there's a correlation between the two. So they are saying, according to these 5 data points, that there's not a correlation between shoe size and height. Make sense? Yes? Okay.
Yep.
All right, moving on. Part 3. Let's look at see what we have going on here. Pause.
We're done.
No.
How do we do number 4?
How do we do number 4?
Let's wait. Let's do this tomorrow.
Let's do 5, 6, and let's do 4 through 6, and then we'll do 9 and 10 tomorrow. Okay. But here's what I want you to do. 5 and 6 are graphing the data, so it's just a scatter plot, and then you answer the questions. What do you conclude about a linear correlation? Here we go. Number 4 though says they want us to estimate what you think an R value would be for this case, right? So the heights are measured in inches, and those same heights are recorded in centimeters. Okay. So over here, I have my height in inches, and I have my height in centimeters. I'm gonna be like all the way over here, right? My height in inches, my height in centimeters. Okay? Let's do like Kellen over here. His height in inches versus his height in centimeters. It's going to be that dot right there.
That should be pretty good.
Should it be
Very strong.
pretty strong, right? Because one is directly reflecting the other one, right? Inches to centimeters should be exactly the same on the chart, right? According to unit by unit. So what would that R value be close to?
1.
Probably 1, right? Okay, because it is a very strong positive linear correlation, right? Okay, so you go through and you look at B and C and D and you figure out what the R value may be. Is it going to be close to 0? Is it going to be close to 1? Is it going to be close to -1, right? Okay, so figure out whether they're related or not and put down what you think the R value would be. Then on 5, graph, do your scatter plot, and number 6, graph and do a scatter plot. Okay, good? You're just plotting data. Make sure you label your axes. Do those 3 problems for tomorrow.
Question about D.
The heights in centimeters and those same heights listed again, but with negative signs in front of it.
Say that one more time.
Okay, so your heights are measured in centimeters.
0.
Okay, but the same heights listed as negative.
So -1.
So it's doing this instead. Yeah? That makes sense? Okay.
Can I go talk to Cleveland?
Okay.
Very
Goodbye, Chloe.
impressive.